I'll begin with a word of prayer. Heavenly Father, we thank you for this day. I thank you again for this opportunity we have just to be together and to think about topology and to try to read this wonderful text by Minetti. Thank you for making it available to us so we can enjoy it. I just pray that you'd be with us today, help us to understand this idea about connectedness in more depth, Lord. In your name I pray. Amen. All right, so chapter 4 in Minetti here is on connectedness and compactness. We'll really just talk about connectedness today. And as I was starting to talk to you guys about last time, the basic issue is here we're trying to come up with tools which we can use to separate, sorry, I was using that in a different sense, to make distinct different topological spaces. Like say if you have two topological spaces, you want to see if they're homeomorphic or not, right? Well, with this idea of connectedness, we'll be able to compare the connectedness, let's say, of these two things and see if it's the same. If it's the same, there's hope that they're homeomorphic. All right? If they're not, then game over. So as is the case with most of these topological invariants, it's usually more good for a negative line of argument than a positive one. I mean, the problem of showing two things are homeomorphic is still, even if you've shown two things have the same sort of connected data, it doesn't suffice to show that they're homeomorphic. But there are some results we get. Okay, so here we go. Definition. And this definition, I like this definition, it's a good definition. Topological space X is connected if the only subsets are both open and closed, are the empty set and the whole set. So X is connected if only the empty set and the complete set are both. Maybe that should be. I can never decide whether this is an R or an is. Oh well. Maybe that's why I got to be in that freshman grammar course. Let's see here.
I think you got it.
But it really has more to do with what you're talking about with that other professor we were talking about. Like some days he's happy, some days he's not. Like that's how my freshman comp person was. It was like some days we were a friend. Mm-hmm. She was just one of the students. It was all like, yeah, it's cool. It's great. And then other days, she was teacher. Mean teacher lady. And I never knew which one I was dealing with. But I'm pretty sure the mean teacher lady assigned me my grade. Let's see here.
Aww.
Yeah, I know. So let's see here. I mean, I don't really care. Maybe I do. I'm still talking about it. Let's see here. The empty set are both open and closed. All right, sorry. I've used precious topology time for talking about English. For shame. It's not like some freshman grammar teacher somewhere is going to use their time to talk about topology.
That'll be the day.
There is some book called Topologies, which is not about math. I was looking for a book for this course and I ran across this. It was some sort of collection of stories or something. And it was not based on the proper use of the word topology in any sense. It's like, what is this? Sorry, I digress. Lemma 4.2.
Wait, is the definition that they're the only ones that are open and closed? Because aren't they normally open and closed?
Yeah, but if those are the only sets which are both open and closed.
Oh, sorry. I thought the only if and then off.
Yeah, the only kind of bleed into that. Now, that is not the definition I remember from my topology course. The definition I remember from my topology course is that a set is connected if it does not allow a separation. A separation of a set, what's a separation of a set? Let me say this is this is equivalent to saying X does not permit a separation. What's a separation? A separation meaning that there does not exist a U and a V open such that U union V is equal to X and they're disjoint. Actually, the thing I wrote on the right, I think, is perhaps a little bit more intuitive, the definition. Right? I mean, think about things that you would this abstraction. As you guys have noticed, we are always trying to find abstractions of common geometric terms in terms of set theory. I mean, that's kind of our bread and butter in here for the moment. And so, I mean, when I think about disconnected, of course, I think about things like this, right? Like -3 to -2, this set, right? And then unioned with something like, you know, sorry, every once in a while, every one of these, it doesn't make sense, I was just checking. 7, 10, I mean, not the scale. So, you know, if that's the whole space, the union of these two things, then it's disconnected, obviously, right? So, on the other hand, if you were to try to, say, suppose you're just looking at one of those, and you tried to find a separation of it, yeah, you could find a union of two sets, right, which covered the whole thing, right? But either, if you do that, their overlap has to be non-trivial. If you just start picturing the open sets, there has to be a non-trivial overlap, right? And if there wasn't, you'd have to use something that wasn't open. Like if I was just looking at one interval, right? And then, yeah, sure, I could find a cover, a disjoint cover like this, right? So like, whoops, sorry. The other notation like this, closed, and then this one open, open, like that, you know? So yeah, I'd have the whole thing, right?
But they're not both open.
But yeah, one is not open. So it's an open cover, which is made of two things which are disjoint. This is a separation. All right, I thought that was worth a second to just talk about. So I did. Now, this lemma 4.2. This stuff is hard to get off. Yeah, okay, fine. So the following are equivalent. X is disconnected. X is the union of two open proper subsets. And the disjoint union. I missed the disjoint word there. Let me add it as a condition here. Not equal. Not
Equal to the empty set.
yes. Thank you. And then X is the disjoint union of two closed proper subsets. And that's your fine print, right? U and V, elements of the topology of X. U and V, closed in X. All right. So far, so good. All right, so let's just pick on the one that is the one I've already wrote up there, right? Can you see why that fits equivalent? Let's assume that X is connected, right? And let's assume X is connected. And let's assume, oh, there's a little fine print that has to be put in here. Non-empty. Otherwise you can run around my statement. So suppose it's connected, and suppose there does exist a separation, an open cover which is a disjoint, non-empty sets. Then notice X, let's see here what we got, X minus with U removed is what? Well, check this out. How about this? X minus with U removed, unioned with X with V removed. What's that have to be?
Exact.
I'm still wondering. Yeah, I think it's the whole set, but I don't know if that's relevant. Sorry, my mind just jumped to that. Let me focus here. What do we need to show? We need to show that either U or V is both open and closed, right? So U is open, right? That's given. Because we're supposing that X is connected and there is an open separation. All right, so we have U is open and we have V is open, right? And what else do we have? U union V is the whole set. And the intersection of U and V is empty. What do I need to do? Now I need to show that either U or V, you pick one, is also closed. How do we do that?
Take X minus, or suppose U is open and then take X minus V.
Oh, X minus V?
Yeah, or I don't know, whatever.
Either one, and you should still try to get them open, right?
Well, yeah, if I can argue that that is open, how would I do that? Maybe a picture is helpful, right? A picture can be deceiving too. I mean, it's an open, so it's something like this, right? So it seems like set theoretically you can argue that X, if we have that U union V is the whole set, which we have, it seems to follow then that X with U removed has to be V, and vice versa. So this has to be U, which is open. Therefore, V is closed. Okay. We can work out the set theory of that. I mean, that's fine. Let's do that. So how do you prove, given, so let me just be more, not just talking through things. So here's a little lemma. Given U intersect V is the empty set, and U union V is what? X. That implies that X, with either one of them removed, let's say U removed, it has to be V. So let's assume assume the precondition here, right? And let's let Z be an element of X with U removed. What does that mean?
X is
You know, would it be?
Right.
of X.
Z is an element of X, and Z is not an element of U, right?
Since X is U union V.
Right, but yeah, right. But X is equal to U union V, and so Z is an element of U union V, right? So what's that mean? Therefore, Z
Element of X.
is an element of U.
I mean, sorry, V.
Yeah, or Z is an element of V, right?
Yeah, and C is not an element of U.
Z is not an element of U, so
Z, element of V is element of X.
that implies Z is an element of V. So that just shows that X with U removed is a subset of V. But I think pretty much the same argument shows the other inclusion. Like if I start with Z and V, right? If Z is in V, that means Z is not in U because they're disjoint. And then because the union of X is U union V, it follows that Z must not be in U. Well, sorry, we already knew Z was not in U. I guess once we've got Z is not in U, then we're done. We don't need to use we actually don't need to use the union idea for the converse direction. We just need the intersection being disjoint. So we start with, you pick like your final write down. So if Z is an element of V and U intersect V is empty, that implies that Z is not an element of U. Therefore, Z is an element of X minus U. And I'm also using, of course, that U is a subset, or well, maybe subset of X, yeah. I mean, I don't know.
Isn't that kind of already implied?
Yeah, I don't know, but you can always write more. Everything I'm doing is ad hoc, sloppy nonsense to a foundationalist. Like a set theorist. Honest to goodness set theorists, they have all kinds of formalism you never see.
All sorts of grammar.
Oh, I don't know. I think I don't have the patience to look at it at this point in my life. Anyway, you guys might still have enough patience to bear it. Or even to study it for your life, I don't know. Anyway, there we go. Alright, I don't mind doing that. It's important for us to do this sort of thing from time to time because that's part of what I want you to learn in this course is how we do set theoretic arguments, right? It's a lot of it. Alright, now that that's settled, I'm going to erase this. Oh, I'm going to let you go.
No, don't erase it. You can erase everything with the lemma.
It's cool.
This lemma, not the 4.2.
Yeah, I got you.
Sorry.
Lemma 4.4. I can't talk. I can't talk. I'm not a ventriloquist. I don't have the power. X be a topological space, and A a subset of X, an open and closed subset. So basically here A subset of X, which is a topological space, with A open and closed. Alright. It's open-minded and closed-minded. Let's see here. I'm sorry, no. For any connected subspace Y of X, what would we mean when we say connected subspace?
Connected under the subspace topology.
Exactly. That's what's meant by that.
It's 4 o'clock p.m.
Silence, woman. Let's see here. Either. She should be careful. She's got no home now. I can't even return her to Radio Shack. It doesn't exist anymore. So here. A or Y. Actually, isn't that kind of a novelty? You used to be able to buy electronics that did single purposes. It's really kind of an antique in some sense. No one would ever take the time to build such a thing as this anymore. Because we've all got these dumb phones that do everything. You know?
You could do an Arduino project.
You do
That'd be
what?
Fun. An Arduino project.
What's that?
Wire it. It's like this little microcontroller you can buy for like $10.
Uh-huh.
Then you can
Really
get these
useful.
boards, various ways to hook them up to other electronics,
Oh.
and you can program it and stuff.
Yeah. It can do anything, but you can make it so it can only do one thing at once.
Huh. Interesting.
I have one you can borrow. I've got like 3.
Hmm.
They're really fun.
Every once in a while, I do get a. I don't know what's the word.
Electronics kit. Like
Yeah,
Project
I get the urge to
Electronics.
go back and like build something in digital. Like after I took digital circuits, I felt like I could build anything. It's just so. The idea of a state machine, you can just do anything. Kind of fun.
Okay, the bottom line said either Y is a subset of X, either Y is a subset of
What have I done? Either Y is a subset of A, or Y intersect A is empty.
A. Yeah, I think the first part you just might have written.
Oh, I see what you're saying.
I think you
I
can
have,
combine what you're going to write next and what you'd written before.
There we go. Yeah. All right. Let's try to think through this lemma here before I get carried away with proving it. We have a subset of a topological space which is both open and closed. All right. Then for any connected subspace, either it's contained in this open and closed set, or it's disjoint from the open and closed set. So it can't be a little bit in and a little bit out. So if A is both open and closed, right, what's that mean? So here's A, right? Maybe that's not the right picture for it, but over here is x minus A, right? So if this is both open and closed, what's that say about x minus A?
Both open and closed.
So yeah, x minus A is, what is that? That is equal to what? Oh, I'm sorry, it is what it is, but I'm sorry, I meant to write x minus x minus. So this is what?
A,
That's A, right? Which is
open and closed.
open. So therefore, this is closed. See, these are both open and closed. All right. So then we want to take a connected subspace Y, right? Let Y be a connected subspace. And then what can we do? How do we prove this claim? Either Y is a subset of A or Y intersect A. My mind is jumping to contradiction, but let me see if we don't need to do that. Let's see here. Oh, duh. I was looking at the example rather than proof is 2 lines. Let's do this here. So he says the intersection, right, if you look at Y intersect A, so suppose Y is a subspace, right? Y intersect A is open. And closed in Y. I immediately understand why it's open. Can you guys tell me why it's closed? It's open by definition of.
Wait, which part is you trying to say is closed?
So the reason that Y intersect A is open is because A is open. Why is it closed in Y?
Y minus A, is that going to be,
Here would be a hypothetical picture of Y, which is actually impossible with the given data, but. What do we need to show? We need to show that Y minus what? Y intersect A is what? It's the intersection of Y and an open set, right? But if you think about that, that's like this piece here, right? That's what's in Y, but not in A.
yeah, so it's Y intersect X minus A.
Right. Y intersect X minus A, you say.
Is that, I guess it's, is that like a distributive property? Or,
Yeah, where'd the X come from?
well, Y is Y intersect X. Right.
Oh, very good, yeah. But, I mean, so, let's see here. If a point is in here, right, that means it's in Y, but it's not in the intersection of Y and A, right? If a point is in here, it means it's in Y, right? But it's not in A. So these are the same set. I mean, and maybe you're right, Daniel. You could just look at this as y is y intersect x, of course, because y is a subset of x. So, but anyway, the point then, of course, is as we already argued, this is open. So what we have then is what? Y intersect an open set, right? So this is open in y, and there you go. So y intersect A is both open and closed, then what does that do? Uh-oh, that's a problem, right? Unless what? It's either empty or the whole subspace. And if y intersect A is empty, well, that's this case. If y intersect A is the whole space, that means that y is actually a subset. Y is actually subspace, a subset of A. And so this picture is impossible, because this picture would actually be exactly have y having a separation. It would have a separation into this piece, and of course, come on, this piece, right? That would actually be a union of open sets in y. Because I mean, this would be a union of open sets in y, because they're both formed from intersections of an open A and an open x minus A. It would give you the whole y, and yet they'd be disjoint. Well, that would be a separation of y, which is impossible if y is connected. It doesn't permit a separation. All right. Okay. And so, example 4.5, we have X a topological space, K a closed subset. Fine, I can't discuss this without writing curses. I think I can erase everything now, actually. So, my personal opinion is the things I've told you, actually, once you hear them, they kind of stick. These for me, these things are natural. I don't know. You can disagree. All right, so this is example 4.5, which I would skip, except I have a suspicion. He doesn't tend to waste words. This example is suspiciously like a proposition or something in disguised, so I'm going to go ahead and cover it, because I have a suspicion that it matters to the larger discussion here. So X a topological space, K a closed subset of X. All right? So far, so good. Let's say U is an open set subset of X containing K. K, so K is a subset of U. This is open. All right, so we've got something like this. Here's X. We've got this closed set, let's say K, and then there's this open set U, which contains K. All right, so far so good. He says if X and U minus K are connected, if the whole space and the open set with K removed are connected, then what?
K is connected.
He said this implies in fact the whole space with K removed is connected. And the rest of the example is a proof by contradiction. All right, so let's try it out. Let's see if we can do it. So what's the proof? So this is actually I would say this is really not as much of an example as it is a lemma. He's just like, oh, I'm gonna mix it up. I'm gonna call this lemma an example.
You mean
That's
lemon?
great. Is that lemon?
Lemon.
Yeah, I was asked earlier what my well, you can't in the linear class's defense. My lemma is really like L squiggle. I don't really try to make the M and the A very okay, proof. So suppose we have the precondition met, all right, and then assume there exists, let's say A, and I'll follow his notation. He uses A and B. A and B, a separation of X with K removed, all right? So in other words, X with K removed is the union of A and B, right? And what? A intersect B is empty. We try to, sometimes I find pictures are helpful for this sort of thing. X with K removed is what? It's like, so you're like basically deleting this from X, right? And A and B would be something like this would be A, right? And then over here would be B. So I think you can see from the picture what's the problem going to be already. If you did that, you'd have this in here, right? And this over here, which would be what? This is going to be, right, U intersect B with K removed, right? This, on the other hand, would be U intersect A with K removed, right? And you can argue that the union, say U intersect A with K removed, right? Unioned with U intersect B with K removed, right? That union should, on the one hand, also be equal to what? U minus K. And also we have the U intersect A with K removed intersect with U intersect B with K removed is the empty set. In other words, the thing in purple provides a separation of U minus K, but we assumed U minus K is connected, so that's impossible. So the question boils down to, do you believe what I wrote in purple? Follows from the precondition. Will you accept my proof by picture? Or have I bullied you? Using Venn diagrammatic bullying into an incorrect argument, I do not know. What's the relation between, so we're taking the complement. I mean, it seems like there may be a property. I really should get like a,
Just a list of all
yeah,
the
just,
different
we just need a
distributed
grand glorious list of every single stupid set theory property there is.
Yeah, I think that there's a distributed property with that.
Right, so I think it would be something like this, right? We've got like X is bad. That's already used, right? I need neutral letter. Pattern is, I don't use Pac-Man enough in here. Pac-Man with K removed, union with Pac-Man. Yeah?
I don't mean to interrupt, but.
Oh yeah, I'll take it. Thank you. Cool. We'll add it to the stack.
I'm surprised you took that so well.
Look at this. He's made me put Pac-Man where it doesn't belong. This was a ghost. How dare he? All right, that's right. No, I was just mentioning to Dr. Joseph, who's scheduling next semester's classes, that one of the things I like to do when I'm in physics lab is look at mathjobs.org. Really makes me do that. That's what my brother said I should say. I'm still waiting to work it into a conversation with Professor Young. Just a little comment. Nothing makes me want to leave here faster than teaching physics lab. Let's see here. But I do think you're right. I think that this is really, it should really just be like Pac-Man, is it like Pac-Man Union Ghost?
Yeah, minus K.
Minus K, I tend to think that that's reasonable. Right, and then, what are the, Pac-Man and the, oh, I lost track. But that's actually, if we believe that,
So it's going to be U intersect A, union U intersect B, minus K.
but that,
The union is just U.
that, yeah.
Minus K.
So that's actually U intersect with A union B?
Yes. And A and B is X.
Yeah, well, A union,
Or X minus
A union B was, what was it? It was,
X minus K.
So
minus
it's just
K.
U right though.
So that's U intersect with X minus K. Which is what? What'd you say? What was U?
No, the whole thing is just U minus K, correct?
So,
It's just like the U donut still.
So U, oh, well, you're saying U is a subset of X minus K?
Wait.
Well, U,
no, I think U minus K, like U intersect X minus
Well, U-
K
U is
just
a-
U
U-
minus K.
I'm sorry, U is a subset of X, right?
Yes.
And whatever's not in U, I mean,
U would cover K, so U disjoint X minus K is just going to be U minus K.
Hmm.
It's just going to be the little U donut up there.
so you're
The
saying,
speckled purple donut.
so this just simplifies to U minus K again, is that
Yeah.
right?
I think so.
Yeah, I think you guys are right. Oh, I hope so, because that's what we're trying to show. And assumably there's some other chain of arguments we can make to show that is in fact empty. I mean, you can read the book too, he's got his own probably clearer argument there. So I'll move on with that. Okay, given what we've talked about here for the first 30 or so minutes, I think you might find the next theorem a little bit shocking. At least I find it shocking that we're talking about what we were about to talk about. The theorem is as follows. It's theorem 4.6. The interval 0 to 1 is connected in the Euclidean topology. Scandalous, yeah. So how do you prove that? I guess suppose otherwise, right? That's kind of usually the case in here, at least for a while. Is you like, okay, prove suppose otherwise, you know? Then what? There exists C and D, open, right? Such that what?
Union D is equal to
Right, so
0.
let me call these C tilde.
So we're looking at like a subspace topology on
Indeed.
C0. Okay.
Yep. So let me just say C tilde, D tilde, actually, honest to goodness, open intervals. Well, I mean, open sets such that C is like C tilde intersect 0, 1, right? And D is D tilde. I don't know if I really need the tilde stuff anyway. I probably could just work with C and D and not lose anything. But those are open in the subspace topology. And what else? So they're disjoint, right?
And their union gives 0.
Right. Again, I'm ignoring his French interval notation. And then let's really do. No, he doesn't use contradiction. Well, he uses contradiction in a slightly different way. I think I'm gonna follow his proof because I honestly I'm a little lost. I don't know where to go next with this current line of thinking. I'm gonna scrap it. Sorry, you gotta know when to fold them. I'm gonna walk away. All good stuff. Let's see here. So we're gonna instead use a little bit more direct argument. Let C and D be non-empty closed subspaces of 0, 1. So basically we're looking at subsets of 0, 1, all right, which are closed, non-empty. No, but non-empty and closed, okay? And, oh, and also what? C union D, the whole set, okay? Thank you, sir. Take that. Then, I don't know, I told them that they can turn their labs in my mailbox upstairs, but it had no effect. Let's see here. So I need to flip this classroom. If I'm lecturing over there,
We'd still see you.
they'll still see me. Darn this door. This window. An animal in a zoo? What is this? Sorry. Where was I? So he says, we claim that the intersection of C and D is not empty. Right? All right. He says, let 0 be in C, and write D is an element of 0, 1 for the infimum of D. Okay, so suppose, I mean, 0 is in one of them, right? So without loss of generality, we can assume C is 0s in C. If C didn't happen to contain 0, then we would relabel C and D. So there's no generality lost in assuming 0s in C, all right? And let D be an element of 0, 1, where, use a little notation here, D is equal to the infimum of big D, yeah. What does that mean?
It's the greatest lower bound.
Yeah, greatest lower bound. So if we had a different book, we might say lib D. All right.
Wait, can you elaborate slightly? Greatest lower bound.
Right,
Say that
so
again.
what we're looking at here is, let's say X in D, such that, let's see here how to say this. x is less than y for all y in D, and it's the that's not it yet. I mean, that's a set. That would be a set of lower bounds. Anything in that set I just wrote is below everything in D, right?
Mm-hmm.
And then what you want is the greatest, let's say max. I mean, max doesn't quite do it justice. Max isn't the right thing to write because the max assumes that it's something in the set. The idea of inf is that you take that, right? Like, this isn't the right thing to say because, for example, max is okay. If this thing ended up being, say, the interval, 0 to 3, right? Then you'd say 3, you'd be fine, right? But it doesn't capture the right idea. If I had the max of 0 and then the set of lower bounds looked like this, then this doesn't exist. There is no maximum to this set.
Mm-hmm.
But the supremum of this set,
It's 3.
yeah, it's 3.
So you said
So
that
I guess I should really say the
infimum-
supremum of this is the supremum of that set.
But you have x labeled as an element of D though. Didn't you just say it was an element?
What have I
of D?
done?
0 to
Could you say it's
Yes, 0 to 1, thank you. Yeah. That's the universe here, right?
Couldn't you say it was an element of the what was it? It's not coming to me. The closure. That would be incorrect. That would take a lot more words, I guess.
Well,
Forget that.
I get it's anyway. It's the like it. I mean, this is a very good description of it. It's the greatest lower bound.
Yeah.
Um,
I get what you're saying now, though. That's the important part.
the thing is, it may or may not actually be in D. Is the thing.
Mhm.
I think if D is
yeah,
closed,
it's closed.
then it'll be in the
Yeah.
closure. It'll be there. Yeah.
And also you put x strictly less than y, but I mean it doesn't necessarily have to be strictly less than.
Oh, I should just have less than or equal to. Yeah, that's actually important, precisely for the max issue. All right. So that's what we want D to be, right? He says it'll be enough to prove that D is an element of the intersection, right? Little d is an element of the intersection. D is closed, right? D must belong to D. So that was what we were just talking about. D closed implies that D is an element of D. Because what we were just saying is intuitively clear that it would be a point on the edge, right? So if D, he says if D equals 0, we're done. Why is that? Oh, if D equals 0, then 0 is an element of the intersection of C and D, right? C intersect D is not empty, right? Otherwise what? D is not equal to 0, then what? Well, D not equal to 0, it says what in this case? In the context, D is an element of what? 0, 1, right? So that means that D is what? D is greater than 0, nothing terribly profound I'm saying right there. And then what he does is he says we set E equal to C intersect what? Intersect 0 to D. This makes a lot of sense. I mean, basically D is the left edge, right? I mean, it's very simple. I mean, I get lost in the definitions and stuff here, but if you really just come back to geometry for a second here, C is something that includes 0, right? So it's like on the left, and then this D is going to be the other piece, right? And if you want to find the thing that's the most left in D, you look at its inf, its greatest lower bound, and then we're just trying to argue that that has to overlap with C. So if the inf is 0, well, that's kind of stupid. I mean, I think what that really would mean is that C and D are the same stupid set, really.
Or the D is 0, 1, and C is just
Oh.
0.
D is 0, 1, and C is just, C is just 0, okay, yeah. But if we look at this, then that should pick up on what then? What is that? E is he says E is closed.
Because it's the intersection of a finite number of close sets.
Right, so that goes back to Euclidean topology, right? So this is the intersection, this is a, I guess it goes back to the Euclidean subspace topology, really. Like Clopin and opposed sets. I don't know, oh, it's interval 0 to 1, so I think it's true, the intersection of closed intervals with the interval are the closed sets in there. Or there's some of the closed sets at least.
Can't say the same thing with open, but with closed,
Yeah.
it's the same thing.
So, but this is closed in 0, 1. C is assumed to be closed, right? So that means that this is closed. All right, so then what? And contains what? It contains, I have to unfrench this just a second here, 0 to D, not included. Okay, yeah. So what does that say? That implies what? That implies that D is an element of E, which says what? It's a closed set. It contains everything in its closure, right? Well, his next conclusion is from this he gets that this implies, so D is an element of C, he says.
Right. It's an element of intersection, it's an element of C.
Oh, right. Oh, duh. Sorry. Why does he have... Why on earth does he have... I don't understand why he has this not included here. That's what I don't understand. Anyway, I'm gonna move on here. So what we have then,
Maybe it was a mistake.
maybe a typo, maybe this is supposed to be, I almost think maybe this was supposed to be this. Because then it's clear to me that D is in here, and hence in here. But, I mean, it's obviously in here, but if it's in here, it also has to be in here because it's in the intersection.
That's the intersection.
Using the fact that the C is closed to get that the intersection is also closed. Okay, well, I'll move on though. So that's huge. So we know what a connected subset in the Euclidean topology is. It's just the interval 0 to 1. So is interesting, I suppose. Theorem 4.7. Let F be a continuous map from topological space to topological space Y, right? Then X connected implies F of X connected. The image is connected. In other words, the connected image, the image of a connected set is connected. Yeah, I think there's hope for this one. So if we look at F of X, so if the proof is something like this, right? So suppose X is connected, right? Meaning that there does not exist a separation, right? Consider F of X, right? The image of X under F, where F is continuous. What do you guys, let me try to do a contradiction again. Let me try. Suppose this is the union of, say, A and A union B, where A intersect B is empty, right? And A and B are open, right? So then, well, you have F inverse of A is what?
Also,
Open, right? And also F inverse of B, right? By continuity of F. But you can argue that F of X equals to A union B implies that X is equal to the inverse image of A union B, which is by properties of inverse image, the union of this and that. Yeah, if I'm ever teaching this properly, the first thing I'm going to do is get just spend like a couple days just making this compendium of every single stupid set theoretic property that exists and is commonly known.
mm-hmm.
Partly as a safeguard against me making them up.
Yeah.
Be like, you have to hold me accountable. That is number what? We'd have our list of like 100. My theorem 97. Whatever. Okay, anyway, that then is a, but,
It has to be the empty set.
what's that?
It has to be the empty set since X is connected. No, wait, no, sorry. The intersection. What am I saying?
That's one way you could go, so that gives you,
yeah, I was
that would give you a cover. I was gonna say,
the intersection has to be the empty set.
yeah, I was about to argue that I think we can argue that F inverse of A intersect F inverse of B
Has to be
is
the empty set.
is empty. That follows because we know that, A intersect B empty. So if you take the inverse image of this, right? That gives you F inverse of A intersect F inverse of B, and the inverse image of the empty set is empty set, so. But then that, of course, gives us then we have a what? We have a,
Contradiction.
yeah, we have a contradiction because now we have a separation of the domain. Oh no, the domain was connected, and we just disconnected it. Not a good thing. So apparently it's impossible. So the continuous image of a connected set is once more connected.